Enzo Di Costanzo podcast. I think this is the 12th video on time value. Yeah, number 12 on time value of money. This is the inflation topic, even though we started the inflation topic previously. So let's get right to that. And actually, before we even start the PowerPoints, there's we left out the self-test here, where the self-test said, here it is. A car loan requiring quarterly payments of APR 8%. What's the effective annual rate? Well, I think we did them all. So let's, we didn't just do 8%. We did we just we remade the table again, which is typical for sort of how I work. So again, I just typed in the 8%. This is formatted as percentage, just repeating that, and then just here I'll do it one more time. I'm hovering or selected the cell that I have the formatting and the data that I want. Shift down arrow and then Control D. Okay, and this other stuff here and here instead of just retyping it. We did this 1 period a year, 2 periods a year, 4 periods a year, 12 a year, 52 a year every day. Okay, so we have all of that, and this is the basic formula. Yeah, this other thing, this example, I don't know if this is cut off from somewhere. It says continuous interest compounding is bigger than daily. Okay, yeah, I was looking for the for where that problem was somewhere. No, okay, I think it's just this. Yeah, it's just the answer to this one. It says back in the 60s and the 70s, the federal regulation limited the APR banks could pay in savings accounts. Banks were hungry for depositors, and they searched for ways to increase the effective rate that could be paid within the rules. The solution was to keep the same APR, but to calculate the interest deposit more frequently. So as interest compounded at shorter and shorter intervals, less time passed before interest can be earned. Therefore, the effective rate increased a bit. And so table 5.7 shows a calculation assuming the maximum APR was 6%. So I think we looked at that already somewhere. Yeah, 5.7, table 5, yeah, down here. We worked this in class, or we worked this in the example. Yeah, that was a 6%. Yeah, example 5.13. Okay, so that's and actually what I'm going to do, and what I should have done, if you guys just bear with me with this. I'm just going to hold on. It's catching its breath as usual. So just hold on a second. Sorry. There we go. So the table shows a calculation, assuming APR was 6%, but it's a round number for illustrative purposes. And then we use the table, how banks are able to increase the effective rate. So the ultimate step assumes the interest paid on a continuous stream. And that's using the base E as opposed to the base 10 or the base 2 system that we're all used to using. So continuous compounding is E to the APR, E to the X. See it over here? It says E to the APR right here, where E is 2.718. Maybe familiar to is the base for natural logarithms. You deposit $1 with the bank that offers continuous compounding at 6%. The investment grows by the end of the year to, yeah. So it's 2.781 to the exponent of whatever the percentage is. So it's a bit more, a few decimal places later, it's just a bit more. That's all we're really trying to say there. So let's see how much of that, because I don't want to start putting in all the E to the X stuff and whatever it might be. It's, as you can see, the APR 6% example increase how banks were able to increase Simply by calculating more frequent intervals. Fine. APR. The interest. Calculate the interest more frequently and shorter intervals. Therefore, effective rate table. Banks could pay with 6%. And we'll just put here previously computed. Yeah, this was way. Needed to move. Sorry, folks. Just give me a second to do a little housekeeping here. Yeah, this should have been moved. I don't know why I did it like this. Yes, it's just this. Much better. Okay. Yeah, you got to again. Again, in my opinion, you're always getting better at sort of how you do everything. Right? You're always getting better at this. The CPI is, and we have some of that. So yeah, so there we go. Okay, like I said, but this other example here, and this actually can go. Yeah, but this other example that we have, this is the 8% table. So yeah, this is the 8% table. So yeah, this is just the 8% table. So we can work through this and say the following. So you're going to take the APR and divide by the M, the periods per year. And actually, the better way to do this is just to dollar sign the columns like that, not the rows. And then you can just say, again, select your cell and say Control D, and you bring the whole story down. All right. And what you can do down here, you can increase the decimal places a bit so you can see the numbers a little bit better. Okay. So all you did there is just divide by the periods per year, that the APR. That's all you did. Again, think of the interest rate that's in the window, the Chinese banks out in Queens, that example that I used in class. The growth factor Yeah, the growth factor would be these rates plus 1, and then the exponent is the m. It's this thing, right? What's in here? See, it's 1 plus APR divided by the m to the m. I just did that right there. And you can take that all the way down, Control D. Oops. Stay in the call. Okay. And this continuous one, yeah, the continuous one is just, this is the I guess the moment that we were sort of waiting for with this. When this is e to the APR, the base e, the 2.71, whatever it is, and then to the 8% is the exponent. So 0.08 would be the exponent. Okay. And then the effective rate, you just subtract 1 from this, from the growth factor. And once again, just Control D the whole way down. And that's what it should be. Whoops. 1 minus that. Whoops. There you go. Okay. So all you did is you took the factor minus 1, which is what you're doing here. That's how you get the effective rate. And that's really what you're looking for, is that. That's really what you're searching for. Okay. So that's just a repeat. We went over this last video. Okay, we're just sort of doing that again. So now that's how to get the effective annual rate. And here one of them we yellowed it out, one of them we bolded it. But here, let's do this. Let's make that bold. Okay, so we've seen that. The next, now you did the CPI. Let's just see if there's any sort of lingering pieces with this. I don't think so. Yeah, this times thing. This was relative to 1950. That's all that this time, and then I think then we did something relative to 1980 for some. I don't know why, but we did something relative to 1980 for some reason. So maybe somewhere in the book it was referenced. Oh, and compared to 1980. But if you could do it to relative to 1950, you could work it out to 1980. So I don't know. This one, who knows? For whatever reason, we seem to want to compute them relative to 1980 for a couple times through for some reason. So we can do that. This relative to 80. Okay, and this will lock the row there. And what does it say here? Yeah, relative to 1980. That's CPI. And then from here, we can just go berserk. What do we do here? This was, for some reason, 2015. This was 2013. 2014. 15. 17. 18. 19. 20. 21. And then where we are, 22. So yeah, we did a bunch. So this is just relative kind of a thing. And also, I was thinking about this the other day about percentages and the times thing. This would be let's find 1, 8, 4, 6, 7. Yeah, this is about 600%, and this is 7 times. So when you're at 600%, this times number is 1 more than the first digit in the percentage here. So if this is 600% more, it's 7 times bigger. So if something is 100% more, it's 2 times bigger. If something's 200% more, it's 3 times bigger, right? So that's how to sort of sort through that. And like I said, so if you're in meetings and people start throwing around these times and percentages, you'll have some idea, because people in investment banking love to throw around the the verbiage like they're NASA engineers, and it's a lot of the times it's simply not so. So just keep that in mind that you're going to be sorting through people who want to appear a certain way. I'll leave it at that. So, but we've seen that a lot. We've seen that over the years. Okay, we'll work on these models in a bit. And actually, what I want to do next is get to the inflation numbers here. So these are the last couple slides for this particular chapter. So inflation is the rate at which prices as a whole are increasing. Nominal rates which money invested grows. Real rates are purchasing power of an investment. In other words, there's a base year somewhere, and you're comparing inflation to that base year, or the change in prices to that base year. This is inflation going back, whatever, 115, now 120 something years. I think did we figure that out? Did we do something like that? I hope we did. We did that somewhere. What was that graph? I hope it wasn't just the index. And this was inflation. Yeah. So how does this look? Does it look similar? This goes back to the 50s. Yeah, we got that first bump, then the next. Yeah, so we have this one, right here. Let's try to put these next to each other as best we can. So comparing, we have the double peak here at the valley, then it goes down a bit, then you have it pretty even with a dip. You have these two, a dip, and this is 2015. And obviously, you had the big spring up here, which we don't have here. But yeah, you had the decline here, you had the dip here. Yeah, this one up, and I think we're here with this. This is right here, yeah. And then this is that other little bump. There's actually two little bumps here, then it goes down. Yeah, so we're pretty good. So yeah, you can see we're reading EKGs now. So that's what we're doing here. All right. So yeah, but that's what. So yeah, so we graphed this already. All right, and now these guys went back to 1900. Some people want to do that. This is a formula. I put this formula on Blackboard for you guys when we started. The nominal rate equals 1 plus real times 1 plus inflation. There's an approximation formula for inflation. So we're going to use this to relate inflation and nominal rates and produce a real interest rates. You compute a real interest rate. The nominal rate is what's in the window of the bank out in Queens. The interest rate on 1 year government bonds is 6%. The inflation is 2%. So what's what are you really earning from this? Well, if purchasing power is being eaten away at 2% and you're earning 6% face value, then obviously the your real rate is only 4%. Okay. And we'll go through the math there. Current dollar cash flows obviously discounted by the nominal rate. So you can't use a real dollar cash flow than a nominal rate. You got to match up the nominal rates and what we have a long example, like another version of the Bill Gates assignment, for you guys. Okay, so please spend the time on that. Okay, it's very important. You guys spend the time in these videos. Okay, it's very important. All right, so that's 5.8, and then now we'll hit some of the Excel examples here, some of the Excel work here on this. Okay, let's say this thing. Open this up a bit. Okay. All right. So what do we have here? What inflation is, real and nominal cash flows. It's an overall general rise in the prices. Increasing the general level of prices means the purchasing power of money is eroded. If the inflation rate is 5%, goods that cost $1 a year ago cost $1.05 today. This is for whatever reason. This is some of the examples here. And this we just typed in 1981, 2013. Now this is probably why we use the 8081 number. So the price of gas during the Reagan year, and this is Barry's second year was right there, and we're using we're using the base of 81. We're using the base of 81. That's our dollar is 81. So we're looking at the price of gas is what we're doing. Okay. And I think what we did did we do? Yeah. I think this is what that column, the 1980 column that I just figured out. So this was relative to 80, and I don't know now if it's 81, right? If it's 81. Let's see. So this is going to be 13 December, and we'll roll up. All right. Well, no, we used this. We did use December. Okay. Yeah. We used. Yeah. It says relative to 81. I don't know why. No, 80. Yeah, 80. But this is 81 for some reason. So here, let's do this. Let's drag this. I don't know why. Yeah, that's 2.5. Yeah, that's 2.5. So for whatever reason, I don't know why we used December 80 when I could have just used 81. I should have used December 81 is what I should have done. But okay. So we have that there. That's 2.5 times is what that is. Okay, so that's where we get the two. Now I 2.48, and again these books, these are not accountants that wrote these finance books. So I would use 2.48, but they're using the book had 2.5. Okay, so and also equals. Let's refer. Let's actually refer to what we're talking about here in 2013. Let's just refer to that. Okay. Yeah, 2.48 times that dollar. Whoops. Times that. That's your 2.48. So the index, and so we want to look at the end. So this is actual. This is what you drive to Exxon. It says 360. The CPI moved 2.5 times. So let's refer to that 2.5 times, and we'll say equals the 1.4. So it really should be 347 or 350. Okay. But and again, you can vary what you refer to in this. So in other words, what you're doing is you're using the CPI change and you're comparing what's on the pump to what the CPI predicted. The CPI predicted 347. The market, supply and demand, the equilibrium came out to 360 is really what that is. And again, what month, where in 1981 or 1980 did we use our numbers, right? So we used here, what did we do? We did 13 and 81. I used December 81, 94. You could they use June, so those are all issues that you can sort of have to sort of deal with. But as long as you know what you used and why you used it, then you're okay. Even if your numbers are off a bit, so the predicted versus the actual, they're off by a little bit, by about 13 cents. This one's 10 cents. Economists track the general level of prices using price indices. Ever see what we did? So in 1981, that's the actual price of gasoline. That's the actual price of gasoline. The index we're using, the base year, is 1. So the CPI from 2013 to 81 is 2.5 times. So 2.5 times, you take 2.5 times to get the price of gas. right? From what that's supposed to be or what it should have been, right? So if you're 140 and 81, it should be 2.5 times, just like the index is 2.5 times. That comes out to 347, but the actual is 360. Okay, so your model didn't exactly predict on, and that's a big 13 cents that's almost whatever, 3 or 4% off, right? So economists chart to general level using the CPI. Okay. And again, the Federal Reserve, they've got a preferred index, and not this one, but the finance guys, because it's easy and it's out there, they use this one. So in 2013 dollars, gas is 350 based on change with inflation. The actual is 360. And yeah, I just said, yeah, the difference. What's the percentage difference? So the percentage, you subtract these two and then divide by the older number. I just said 3 or 4%. So it's a 3 or 4% difference. I just said that. Okay. And yeah, this explains that the index was 2.5 times of 81 level, 2.5 times 140. Yeah, so this says it in words what we just did. Okay, the change over the 32-year period. Okay, and then we certainly could. I didn't update this, so we could take today's numbers and up. But that's, you see the exam, you see how this works. So you very easily can work on today's numbers. This is another one that's similar. This is the 2015 example, where we're using, again, our base is 1980. It's a dollar eight, I guess, in 1980. Today it's 2015, it's $2. Okay. So again, how do we get the 2.74? So yeah, this is the 2015 one. All right, this is 2015. So this was the actual gas prices. So yeah. So again, once again, you want to take a look at sort of what it should be versus what it is. So again, the index change, this is going to be the change in the index. Then you'll apply it to that number, and then you're going to make your comparison for a second time. So let's see if we can figure out, where we got the 2.74 from. It was 80 was 0. Right there. And I don't know if it's 469, but I don't know, 80. Yeah, no, we're back in 80 with this one. We've got the right one here. Yeah, 2.74. So it's good. We see this again. So this equals, what does it equal? Yeah, this equals this times your 1980. Right there. So you have and then what you do is you equate that CPI change there, and then you apply it. You say 108 and 24, and again, you should be 296, and it's only $2. So these are the ones you're comparing, right? You're comparing those two, and same thing here. You're comparing those two, and then you got your difference there. And again, for better or worse, so we had these, we left it in there, but all the differences, you subtract them and divide by the old one. That's all that happens there, is that. Okay. But again, we went through the same process a second, which is good. It's good. It's good you saw how to do this. So the CPI in however many years that this is, 35 years, right? What is that? Yeah, 35 years. So now these 30, so 2015 is pretty close, like I said. So we did two of these. You got a third one. It was one, guess it was 108 in 1980. It was $2 in 2015, right? And then, so 2.74 times change based on the CPI. And then you apply the CPI change to the dollar rate relative to 2015, and 2.74 times the dollar rate should be 296. There's only so we were off by about 50% the model. So these models, we like a model, but this is the same conversation. Again, $15, 296 based on the CPI changes with inflation. Gas was only $2, and the difference was 48%. And you saw the 2.74 times with the CPI. Okay, with what this would have cost. But the price of gasoline actually declined over the 35-year period. Okay. This one, it's a phone call to London. So the price, God knows when with this, 511. So we're talking about 50 years ago. Or in 50 years. Yeah, it says if the real price doesn't change, what will it cost in 50 years? So we're looking at 50 years, right? Which is what that is. That's 50 years. Okay, 50. And actually, these should be blue because they're typed in there. Inflation's 5%. And then you have a 10% model. You have a 5% model, you have a 10% model. And the price of whatever the phone, and folks, like I said, when you travel internationally, be careful with this stuff. Okay, because these prices can really hit you. So if it's $5 times, and now it's the same math that we started the course with, 50% and then 50. You're looking at $57 as opposed to $5. That's how much. And I think in class I used the price of my dad's car. His car cost whatever, 2,000 in the 60s, and what would it be today? And so, okay. So $5 at 10% is 586. $5 at 5% is only 57. You can see a whole order of magnitude bigger, right? With a little bit of a different, which doesn't seem like a doubling, inflation of 5 or 10% doesn't seem much different. Look at over 50 years what that does to the dollar amount. Okay, but that's the impact of inflation. This is like the example that we used in class, the price of my dad's car from long ago. Okay, what is this graph here? All right, that we don't need. The graph isn't. Yeah, I apologize for the how jumbled up this is. Expenditures in nominal terms. You take 1990 as your base year. Okay, 90 is your base year. So, so what do we do here? I think we use the CPI numbers for 1980, 1990. Pardon me. Yeah, so we use 1990 right there. Okay, we looked at that one. Return. So what you did is we took the December 1990 CPI, a good year, all right, and then we compared it to 2015, right? Whatever we had in 2015. So this is going to be locked. Control D, and this numerator, you can just go find what 2015 was. And there's 2015 right there. Okay, 1.77. Yeah, so you took out a mortgage. This was taking out the mortgage in 1990. It cost $800 a month. and then 2013 or 2015, really, how should that have changed? But if you're paying nominally, unless you have something that's which I don't know if those products even exist, where, hey, if inflation, I don't think they do. It says, well, if inflation hits, you're going to be paying more. You're going to be paying, whatever it's 1990s dollars, kind of a thing. Even in 2013, and as the 2013 number changed, you would change what the equivalent of eight. You're not going to pay $1990. You pay $2013, but whatever 800 bought in 1990, that product, whatever the price would be in 2013, which would be more, you're going to pay that. Usually they're nominal. Where if you're paying 899, you're paying 800 in 2013. Even though if inflation hits, then obviously it's good for the borrower because you're paying in dollars are less valuable. So you hear those kinds of arguments a lot. Okay, because what would happen was if it was inflation, I mean, inflation adjusted is good for Social Security. It's good for if you buy some kind of fixed income product, and all of a sudden, as inflation impacts it, your payments increase with that. But the reverse would be bad for you if you're the borrower, and all of a sudden, you've got to pay $13 for what $800 bought in whatever it was 1990, and then that same what it's worth today. Here, I bought a case of I like the seltzer from ShopRite. It was on sale, 12 bottles, 12 1 liter bottles were $4 20 years ago at the Nutley ShopRite. Now they're $6. It's the same 12 bottles. I told the woman that at the checkout. I said, these are the same 6 bottles, they're the same 12 bottles. You know that? She goes, oh yeah. So, and then she was telling me some of her life story as I made the mistake of talking to her. But so yeah, so looking at this, so obviously if you're paying nominal rates, you're going to pay $8 30 years ago. You're going to pay $8 or $800, now over the whole 30 years of the loan is really what this. But what would this look like in the night? It says, well, in real 1990s dollars, it's 2013 dollars is really what it says. What's the monthly payment for 2013 expressed in real 1990s dollars based on the CPI? Okay, so in other words, what $800 bought in 1990, whatever is going to buy, some other number today would buy that. Okay, whatever the 2013 number, and let's go right to that. So you're paying 800 in 1990. You're paying 800 here. So looking back at this, and again, it's all the perspective. I did what the book sort of wanted us to the approach of and again, like I said, you can make all sorts of arguments with this as you go along. So whatever that was, 25 years ago, you made an agreement, that was your base year. So how I would look at this, just sort of looking at it again, this would be 800 times. Yeah. So what I paid 800 for 1990, 25 years later, I should be paying 1,400. So if I'm still paying 800, I'm making out better because the CPI changed by almost 2 times, which brings it almost to 60. But I'm still paying the 800. Okay, or looking back, kind of a thing. And I'm not sure how much sense this makes, but what these guys did was they said, okay, well, we're still paying 800 today. In 1990, what would that 800? What would you have needed for in 1990? The today cost 800. What would have cost 25 years or previous? So if you look at that and how this sort of works out, you're going to take this divided by that. Yeah, that's the 425. Okay, so in other words, looking at this, and you can you can back out that number, and I'm sure I'm sure that's what this is over here. Yeah, you're going to say equals 1.7 times. That's how you get to the 800 today. But the problem is you're still paying 800 in 1990. See what I'm saying? So, like I said, so you have to have the fundamental idea here is the following: as a CPI changes, you can multiply that times change by any kind of dollar amount to determine, okay, what I paid $4 for in 2003 and 2023, I'm paying $6 for. So and then compare that to the CPI. And actually, let's see. While we're sitting here, let's do that. Let's do the seltzer example. So we did 184. Yeah, I did 184, and we'll get the current something. So we'll do copy, paste. We'll do equals the December number here, 203, 1.6 times. So we'll say equals 4 times. Yeah, actually, we're getting a better deal. That case of seltzer should be 644, and it's only 6. Actually, the sale price is 6. So it's actually the normal price is more, but the normal price was 480, or I think that the normal price was maybe $6 a bunch of years ago. Right. And now, yeah, it is about, yeah, we're in the area with these numbers. We're in the area with these numbers. Like I said, so the first one was, I think, the best example to look at. These guys, they try to go in circles with these sort of examples of CPI and all these other kinds of things, and I try to make it, I try to I try to work out the numbers as best I can. Yeah, let's get rid of that. Yeah, I try to work out the numbers to be consistent with the book. And like I said, so I don't know, making this kind of an argument, looking back, saying, well, I paid 800 25 years ago. What should I have paid if I'm paying 800 today? That's really what this problem is saying. So I don't know the usefulness of that. But like I said, if you have some sort of debt instrument and you're paying 800 a month or something like that, that's good, because if you look at the CPI of over 25 years, that 800 should be a lot more today for what the bank is. So in other words, you're paying the bank in the same in $1990, and it's their 1990 value, and that the money's not going as far 25 years later as it did, back when who was Bush number one was president in 1990. Okay. And what does the book say? It says in real dollars, it was 452. Sure. So what was the real in 2015? 800 was real at 450. Okay. So yeah, we're just going in circles with this stuff. So, okay. The next thing, this is, I think, a similar example, and then we'll go to some of these other ones. Self-test 512. A family spent 250 in 1950. How much were those purchases in 1980? Cost of the salary in 1980 was 30,000. Will be the real value in terms of $1950. And again, we're utilizing that the CPI table, which I think is good. So, all right, let's take that one at a time. So 250, 1950. Okay. So this starts with, you spent 250 for whatever. Water, gasoline for the car, bread, chicken, beef. You spent 250. Is it weekly? A week. Okay. I don't spend 250 a week, that's for sure. All right. Yeah, so we take the 1980. Yeah, I forgot how much we use the CPI table, so it's good we sort of updated it. 1980 CPI was right there, and divided by del B 469, which was right there. Okay, what's that? Okay, which is that? All right, so that's the 80, the 1981 is that one. Or, oh, I'm sorry, not 1980. That's 19, this should be 1950. Yeah, these should be the 1950 ones. Sorry. So this is whatever it is. We'll just type it in. This is 109. 109. Okay. Right, that's 109 is that. And this is 469. Yeah, 1980 was 469. So, yeah, what do we do? We referred here, and we referred there. Okay. So what should this be? This should be this times the how the CPI changed. So again, the essentials that a family was paying 254 in 1950 should, 30 years later should be costing, 863. And it looks like we don't have a big long. I just did the table. We don't have a big long discussion on it, which is fine. Okay. And then the other part of this was if the salary was 30,000, what's the 1950 version of this? So if you're at 30,000 today, all right, what's the 1950 version of that? So you're here, 109. And this is double B. Yeah, so you have the same CPI change that you had previously, and you want to figure out how this grew. Well, what you would do is you would take this and you divide by that 3, which is that. And then we did some kind of check here. Yeah. We took this times the 345 and got the 30,000. So I don't know, we're just moving this thing. As long as you understand, looking forward, I think is the better way to do it. But you can look. Some of them look back and say, "Oh, was it 1950s dollars?" And this is not. These are 1980. This is 1950. Okay, so I don't know what. You could say, in 1980s dollars, what you paid for in 1950 was 30,000. You could make that statement. But like I said, you got to be careful what you call, because people, the media jumbles this up a lot because they want to sound like everybody wants to sound like they're an economist. So you got to be careful with how people sort of describe all this. Still good. Oh, yeah. So we have 7 short ones, and then we sort of have a Bill Gates version. We're spending over 30 years, and that's good. That's the midterm assignment is that. So let's sort of hit some of these as we go. I could have probably stopped the video right here, but let's just sort of keep going. You can hit pause with this. What a nominal rate is money invested grows at actual dollars, and it's not offset for future inflation. Real has an inflation adjustment in there. That's what that means. Okay. So if your nominal rate is 6% and you have $1,000 today, and inflation is 6%, and again, I should have had this worked out here, and I will. The real rate equals parenthesis 1 plus the nominal divided by 1 plus inflation, and then subtract 1. So again, so if you have if you got a 6% inflation rate and a 6% a bank product, the bank's not making anything, or you're not really paying anything because your dollars are deflating at 6%. Yeah, the value of each dollar is deflating at 6%, and so you're paying the bank back in less valuable dollars. Okay, so how do we do this? So the nominal balance. So if this thing grew in just let's look at this. Is this in your bank account growing? This is just simply this, right? It would turn to 1,060. Okay, but let's look at the real version of this. Yeah, the real version, just you divide by inflation is really what you do. I mean, there's a couple ways we can do it. I said this equals 1,000 times 1 plus 6, and then divided by 1 plus 6. Okay, so the real future value is just that same $1,000. Okay. And we did it another way. I don't know why. I just went like this. I took this number, which is the same thing. I don't know how that's different, but still $1,000, right? So, but like I said, this is I put this formula on Blackboard, right? This 1 plus real times 1 plus. So again, as long as you have the basic formulas, you can work your way through any of these problems that sort of come your way. Okay. Yeah, here's the real formula. This is what I just did. Just so okay. This version has a 6% inflation. Whoops. This version has a 6% inflation rate. I'm sorry, nominal 6, inflation is 2. So the real is going to be equal parenthesis 1 plus nominal 1 plus inflation minus 1. This is 1,000 equals this 1 plus the nominal rate is that. I want the real numbers equals 1,000 times 1 plus 6. Is that? It's truly 1,039 is the real future value because that's the inflation adjusted number, or you could just say this. Yeah, and it says it in words here what that all really is. So you're adjusting for inflation by dividing by 1 plus the inflation rate. That's really what you're doing here. And this is the self test. This is all the same stuff. Let's look at the self test. But this thing invested 8%. What's rate if inflation is 0? What if inflation is 5%? What if you demand 3%? What's the nominal rate you need to? So yeah, there's a few questions here. So I don't know if I put this in the man, there's no room for it here. So what are we doing? Yeah, I moved it down a bit. This is I don't know why we have that, why I'm even leaving this in here, but I'm leaving it in here for some reason. So okay, I'm gonna have this copy. Okay, we did a little moving around of everything, and I can do that at some other time here, I suppose. So. Actually, what I could have done here, I could have just moved this up. Okay. I put the questions in here, so just so we had it a little bit. So what do you have? An 8% nominal rate. You have $1,000, and you have 0 inflation, and then you have another example here where it's 5% inflation for 8% and 1,000. All good banking examples. This is all good banking stuff. A lot of detail, right? A lot of detail. So, and what's the question? It says, what do we funds? Okay, what will be the real rate of interest if inflation is 0, if inflation is 5%? Okay, so yeah, obviously we have an approximation there. So this is going to be equal to parenthesis 1 plus nominal 1 plus inflation 8%. 8 minus 0 is 8%. Okay. Yes, let's solve for this. And this one I'm just going to copy and paste. Same thing. 1 plus 8% divided by 1 plus 5% minus 1 is 2.86%. Okay. So now this is the same math that we previously looked at. 1 plus 8% is that. Copy and paste. I can just copy and paste this here. It's the same thing. Right there. This we're not going to need. We're going to need. And then and I could even just leave 1 here. I don't need to keep repeating myself here. What we could do is just say equals 1,000 times 1 plus nominal divided by parentheses 1 plus inflation. 1,080. Don't worry about doing it another time. And same thing with this. Copy, paste. 1,028. This is 1,080. So if there's no inflation, it's just 1,080. If there's some inflation eats into it, the real value is 1,028. It's not what 1,080 would buy. It's what 1,028 would buy. Okay. And then these approximations, this is just the difference. Just you subtract 8 from 5, just get a quick approximation. I believe me, it's not that much work to get the 2.86. And this other part of it, Here we solve for the real, and the other one is suppose you rate. It says what's the nominal will be, and actually for this one, you're solving for the real rate of interest, and this is the nominal. Okay. So if inflation here is 0, inflation here is 5. So now the inputs are 3%. And actually these should be blue. All right, and this should be, because what you're doing is you're backing out this. You're backing out the nominal rate. So the nominal would be equals 1 plus the real times 1 plus the inflation, and then subtract 1. And I'm just going to copy and paste that down here. Okay. When you have 5% inflation and you want a real 3%, you got to have a nominal of 8.5, right? 0.15. Okay. Oh, I have 2 of these. There's just 1. Okay. And then we could do this all the same stuff again. 1,000, 1,000, and see what this all is going to look like. So this thing is going to grow to equal to 1,000 times parenthesis 1 plus the nominal rate, which is 3. And then here equals 1,000 times 1 plus nominal rate divided by 1 plus inflation, which is 0. And we can just bring that down here again. And bring this down here again. All right, just clean those up. Okay. And like I said, we could, but this is good enough. I repeated it. I repeated. I don't know why I kept repeating the calculation there. So, but this is good enough as to how to do this. Like I said, so now you're utilizing this formula. You're utilizing the inflation adjustment formula, and you're going to get a good sense. Hopefully, you get a good sense of it. It's complicated. Okay, it's not simple. Okay, it's not simple at all. So. This thing is a repeat for that's just extra in there for some reason. I don't know why. So, and then here, this is a big long net worth type of, this is spending, I don't know, some amount of money, and we're gonna look at how to do this. But again, we've already faced this already, but we'll do it again at the end of today's lecture. So, anyway, this is the approximation for real rates. Okay, it works well when inflation rates these things are small. Okay, but we still like that formula. Okay. So what do we have here? This is at the time 5.71% bond. You had a 1% expected inflation, right? You had that. So the approximation is just simply the difference. And actually, do we have difference? We have that as a formula. I don't know. Do we have that? I don't think we have that. So I just subtracted them. You got 4.10. The formula is equal to 1 plus So you can compare what the actual computation and versus the approximation, what that's doing for you. Okay. We have valuing real cash payments. This is next. And this is another. Yeah, the Bill Gates thing, we went back and worked out the Bill Gates problem. So I'm not worried about the Bill Gates problem. That one, I'm saying we already did this. Right? 516 was already worked out. This example is 10% nominal inflation. We expected at 7. What is this book talking about here? It says what's the real value? What a year earlier you spent $100 on, a year down the road it'd be you have to well yeah, what costs 93 today would be 100 a year from now. That's what that means. And like I said, they try to, like I said, they talk. I always try to go in one direction with everything. They try to go backwards and forwards, but it's now certainly and it says the real value of is therefore only 93. In a year's time, it only buys as much as 9. Okay, that's another way to look at it, right? So yeah, what you're that's what I just said. We spent 93 today is you spend $100 a year from now. And it goes through the math of that, you know, one more time, we sort of do the mathematics of that. So when I'm spending 100 a year, and I think this version is just the nominal. Yeah, this is just the nominal version of this. This is the adjusted version. Yeah. So this would be equal to this divided by 1 plus nominal rate, and the exponent is a year. Right? So just without inflation, expect to spend $100 a year from now on something that you spend 91 today. That's really what that means. Okay, this other version of this, we took 100. It says, yeah, today is worth 93. Or yeah, another version of this is right. So looking, and actually this is already worked out for us, but yeah, this just takes the 1 plus nominal divided by 1 plus inflation minus 1 is 2. The real rate would be 2.83. So the version here, how do we do this? This is 100 divided by 1 plus inflation is 93. So yeah, this is just showing the impact of inflation is really what this is. So this is equal to divided by 1 plus. And you could just say that, but I put the exponent in because we have it. Inflation would make 93.46 grow to 100, where if it was growing at 10%, you'd only need 90.91 is really what that is. But again, just illustrating some things here. So we're going to discount 93 with the real payment by 2.8%. Okay, so yeah, so in a sort of in a roundabout way. So now what we're doing with this is we're going to take the 91 at 100. Yeah, now we're going to discount this one more time. Yeah. So yeah, it's doing it in steps. It is really what this is. It's just doing it in steps. So and then how to get that 91? You take the 93 divided by 1 plus the real rate 1 to 1 power. Yeah, that's how you get the 91, and then you're just back to which in a very triangular argument. So in other words, you took the inflated number, and then you applied the real rate to it, which is sort of another way to do it, which is not. I don't run this route. like this. I don't say, well, let's see how inflation impacts cash, and then we'll apply the real rate, because it almost feels, even though it's not, but it almost feels like I'm doubly inflating it. It feels that way, even though it's not really. But you can see though, you get back to the 90.91 is really what you're doing. So, well, this is another way. The book does. I don't take this route too often. Yeah, we repeated this for some reason. I don't know why, but we repeated that. And then this other version here. Yeah, this other version here does 8%, 5%. And this is what this is self-test 514. You're owed 5,000 by a relative. We'll pay it back in a year. The nominal rate is 8%. Inflation is 5% with this, or in the world. The present value of the relative's IO, you're owed 5,000. Same mention discounting nominal payments and discounting the real payments. All right, so you have 5,000 in a year and 5,000 in a year. This, again, we sort of did the same thing. You know, you could equals this divided by parentheses 1 plus 5,000 or 1 is that 4,761. Okay. And again, we did the same. This is 8 and 5. Yeah, this is 10 and 3 or 10 and 7. This ain't, so that you can see the difference is the same. It's still getting 2.85%, about 2.8 something percent. Fine. This is equal this thing divided by parentheses 1. Right there. 4629 was that one. This equals that 5 that you get to. And I think what we did here again, we said equals. What did we do with this? This was, yeah, that 93. This is the inflation number, right? And then you divide it by 1 plus the real rate to 1 year. And that's how you got the 4629. Yeah, discounted nominal payments and nominal rate found nominal. Discounted payments, the real rate found real. Okay. And if you guys will just, again, be patient with me while we do this. What I want to do, I'll just put the question in there. All right, let's center this. This is the midterm. It's another version. So again, the people who really watch these videos, you'll get another sort of practice at this, which I think will be a healthy, good thing to deal with. There we go. Okay. Yeah, so this was another, you do the inflation adjustment and then you divide by the real rate, and that's how you get the 4,629, or just take the nominal and divide it and still get the 4,629. Now you're using real rate, and this uses the nominal rate to get these numbers. But this is the inflation adjusted number of what that 5,000 is going to be. Okay, well, like I said, yeah, you got to practice these for all this for it to sort of make a lot of sense. All right, so we use the Bill Gates example, and now this part here is it says we showed an early example that an interest rate of 6%, it could, if he wished to turn his 67 billion to a 30-year annuity, it would be about 5 billion a year of luxury and excitement. So the L&E expense inflates just like gasoline and groceries. It finds that the purchasing power is declining, so he wants the same luxuries and he'll have to spend in 2013 and then increase expenditures in line with inflation. So how much is, yeah, so looking at this, so we did the real version. So yeah, this is just, we did this already. Okay, remember, so we had the 3.374, and let's just go back and make sure that we're all looking at that same thing. Yeah, this is whatever this was, 398. Yeah. Yeah, I have 7.9, right? I have 7.9. The book has through 7.9. And this was 67, that example. Yeah. Okay. So, and we had 4 something here. Yeah, 4.9. Yeah, 486. So yeah. So like I said, so we previously worked this out. So this you've already got this worked out in another video. Okay. This was good. We use the CPI table and some examples. You saw that. And like I said, our last problem of this lecture is so we looked at the Bill Gates one. So it's a self-test 515. You want to spend those amounts. Okay, so what we'll do again, just to give ourselves a bit of room here. There, a modest fortune of 3 million, next 30 years. You have nominal rate, you have an inflation rate. And here's the real question. Okay. One, two, three, four, five. And we'll box in, some of these other descriptions as we go through this. But it's another annuity problem. Okay, this is another annuity problem, is what we're looking at. The nominal rate is 10%. And we don't have inflation here, but the long run inflation is 5%. And you're looking at 30 years. And you're looking at 30 years there. Okay. So you have all that. And you're going to back out the real, you'll back out the real rate. Actually, here, let's get rid of this thing. We're going to compute this ourselves. It's this, the 1 over R. It's this formula that you saw previously. Okay. So let's see. I have 3 million. So you start with that amount. And the factor based on, now this is just nominally doing it, equals parenthesis 1 divided by R, 1 divided by R again, and then we'll do 30 years with this. What that means is I need, or what does this mean? Okay, I need $9.42 if I can earn 10% and I want to spend $1 a year for 30 years. I need $9.42 today to earn 10% a year, and I can spend $1 a year for 30 years. That's what that means. And then from here, to get the cash flow is just simply the 3 million divided by the rate, and it's that. So that's what you can spend. Not bad. Not bad. And here we have it in there. Stream of cash flow payments. Okay. And then here we can get down to this. The start of the years and whatever it is. So your initial, so this was year 0. Your initial balance was 3 million. That's it. Okay, which was that? Let's add 1. Right, we have 30 years of payments, or when we're planning on spending at the end of the year. This equals to 3 million. The payments we've computed, right? It's a 10% nominal rate. The payments are that 318. Control D. So this is 30 of them. Okay. And the interest number would be the whatever's here times that 10%. We'll lock this in. Okay, so you're going to earn that. And the balance would be the million minus the payment plus the earned interest. And this is just simply that. The remaining, I don't know why I have 2 columns, but they just stopped with the remaining balance. But I did another one. And then you snake it around here. All right, you snake that around. So the whole way down, you can do that. Don't worry that they're not filled in. Okay. And this is the rate. So this will do, actually get all three, copy, Alt H, the formula. Okay. So we're here with this. Yeah, 2.61. Yeah. Okay. So now you have 2.981 million. You earn 3%. It's 298,000. So you earned a little less, but still, this built up. So this interest earned almost matched the payment. This interest earned almost matched that payment. So you're pulling out 600, and you're almost making that. A little less, but it diminishes over time. Now what you can do, you can just do this, Control D, and there. See how you end up with, as long as you're ending with 0, you did it right. That's how you know it's right. Okay, the book didn't do it. What did the book do? And the book just look for the answers, I think, somehow. Yeah, here's. So this is all they cared about was the real one. They didn't even ask for the nominal. So we worked out the nominal. So they didn't even put the answer there. But we'll get to it. We'll get to it. But this is the nominal. So for the assignment, you got to do this. This is one of the things you have to do. The book wants this. The book wants this one. So $15. Okay. So now the real interest rate would be equals parenthesis 1 plus nominal rate, which is 10 divided by 1 plus 5 minus 1. 476, and you can increase this a little bit. 7619. Let's look in the book. Yeah, 4.8. Yeah, the real rate is 4.8. Yeah, 4.76. All right, so we're right there. Okay, we're correct on that. The factor, instead of typing that big long complicated formula, we'll click in here and we'll connect this to. This is the 30. This is this rate. This is this rate, and the 3 rates. Okay, the factor is 15,798. Again, the book used a little bit different, but 1572. Okay, close. We're close. And then the spending would be the 3 million divided by the factor 189. Yeah, 190. Okay, with a little, So I don't know what this 210 and this 200. I don't know what all that stuff is. Yeah, they're doing inflation adjustments. So you get more. It says you have to spend more. That doesn't really make any sense. But okay. I know what they meant. Yeah, you can, but the purchase power will decline 5% a year. Right. That's what that means. So now the spend will increase. Yeah. Okay. So again, just you're kind of going in circles. Now you're going in circles a bit with a lot of this as usual. I think we already looked at this. What the spending in the second year would have to be. This is, yeah. You're getting the 189. That's what you're getting. So, and what it buys will get eaten into at 5% a year, by 5% less a year, because things cost more. Okay. So your initial balance, same 3 million. And there's no payments. And actually, what we could do here, copy your 30 payments. This equals that. And the payment now, it's not 318 anymore. It's a little bit less. All these 189s here. And now this is all the same. All right, this is all the same model. And now, but instead of that 10%, right, I think it's the real rate, right? F4. Yeah, it's the real rate. $. E, these you need. Okay. So you have a payment, you earn something. So your balance is you start with 3, you earn the 142, and you subtract out the payment. This equals end of the year balance. And these both need $signs. I don't know why there's no $signs here. They do. And we'll copy formula only. All the way down. All the way down. And again, zeros. Because so this again, this is how I understand it, how I approach it. But like I said, the book has came at it from a couple different angles. Okay. But there you go. So that's the end of the time value of money parts of the course for the spring 2023. Okay. So it's all worked out for you. So you can see the answers and the numbers, and you can stop the video and check all of your answers down here. Make sure you stream down, right? And you got to go line by line, piece by piece, step by step. You have the nominal part, you have the based on the real interest rate, right? You have all that. So always save your work, just always, all of us, myself included, right? Okay. Now, is this the 2015 model here? Yeah, I don't know if this was the 20, because the Gates thing, we did the Gates thing already. We did it in previous um, lectures. Okay. All right, folks. So the PowerPoints, we got through all the PowerPoints. So the next set of lectures are going to be the Federal Open Market Committee December meeting analysis. You have to watch the press conference, and there'll be a bunch of questions. I posted the Microsoft I posted the midterm. I posted that for you guys already, so that's already up online, so you guys have that. Okay, so you guys should be all set. But there you go. So I hope you learned about something about time value of money from all this. Yeah, again, so I hope you learned something about time value of money from all of this. Important, and I do a lot of valuations in my work, and it's extremely important to be able to do all this, and put it to good use, and as your careers unfold, and you don't know when you're going to need it. Okay, because it can pop out at you at some time, and but yeah, I've been an analyst for my entire career, and I've enjoyed that. I like it. I excel at it. It's all this. It's what I like to do, but it's not for everybody. Okay, it's complicated, messy, a lot of details. Okay, but this is what this kind of work looks like, and if you excel at it, it can be very valuable. You might get your CFA exam or your CPA exam, or might be engaged in this work at some point in your careers. Okay, so you don't really know. All right, folks, take care.